sequence. So yeah, just should this also be recorded or
Yeah, I forgot actually. I'm just recording.
Yeah, just a reminder.
Yeah.
Okay, so just to start very quickly again, due to the recording here, today we'll talk about modeling and specification, and we have shown the automata descriptions, especially the synchronous composition, which is a critical part. And then we will talk about verification of a system where you have a plant and a controller and a specification. And the verification is to verify that the specification satisfies the closed loop system where you synchronize the plant with the controller or supervisor. Then the main topic for today is the synthesis. The synthesis means that we automatically generate the supervisor or controller to satisfy the specification. So then we introduce some specific notations or notions here as a background for the discussions today. So first, we assume that we have a plant, and you see here that I used a superscript here to identify the elements in the automaton. So QP is the set of states in the plant, etc. Note that the plant does not include any marked states and also no forbidden states. I consider that as a part of the specification. So here the specification includes also states, events, transition function, initial state, but then also marked states and forbidden states. This is not the traditional way to consider it in the literature, but we argue in our group at Chalmers that this is a more natural way to think about specifications, because specification is something you would like the system to fulfill. And then the plant has its full freedom, and your and our task is to restrict the behavior of the plant. And those restrictions that are necessary are given by the specification. And they are, in terms of desired behavior, the marked states, and also forbidden, undesired behavior by the forbidden states. I have called it QF instead of QX there. Then we have the simple example of a plant and a specification, actually the same example we have shown before. So the plant with A followed by B or C, and the specification, well, in this case, it's actually not exactly the same as we did last time. Now I would like these choices B and C to be taken every second time. So first, when we have made the A in the plant, which is a local event in the plant, then the specification says that take the B. When you have done that, you can make one more local A, and then you are in the second state in the specification, and then you should go back with a C, which means that you take the alternative decision the second time, and then you repeat this behavior. So then once again, B and A, C. So that means that the synchronous composition of P and SP will be then A, B, A, C, and then you repeat this. Why is both the first and the second state here marked? Well, it's because the specification is still in the first state, and there you have the marking. That means that the plant can be either in state 1 or 2, 1 here or 2, and that is still a marked state in the closed loop system, or in the synchronized system with the specification, is more correctly to say here. Now, these specifications, which in this case were, I mean, it's an extremely simple example. It's what we call a local specification. But when you take this specification together with the plant, you get what we call a total specification. This is exactly what we would like the total system to behave. And that is called S0, not S total or something. Why we call it S0 will be clear a bit later on here. But let's see what it said, the text here. Yeah, okay. It's called the total specification, but it's also actually a first candidate of a supervisor that can control and restrict the plant such that the local specification will be satisfied. And that's why I call it S0, because it's a first candidate of a supervisor. Now, it could be that this first candidate has some bad behavior in terms of, for instance, blocking states, meaning states from which you cannot reach the goal or marked states. And those states are, of course, not acceptable. So those have to be taken away. And then you could say that this first candidate need to be analyzed and simply remove the bad behavior in that. And that is the simple procedure for synthesis. So we have already a clear idea of what we would like to achieve. But to add to this, we should also include these, as I mentioned also yesterday, uncontrollable events and other things. So it will take some time to get the final solution. But the general idea is that you start with the synchronous composition of the plant and the specification, and that is the first possible solution for the supervisor. And then we need to look at that and see if we need to manipulate it a bit to have the perfect behavior. Now we also take some specific assumptions regarding the event sets or the alphabet, as why they are called the alphabet is just that it's a notion from formal languages. So the set of events or set of actions, they are called the alphabet. So the alphabet of the specification is now assumed to be a subset of the alphabet of the plant. And that's quite natural because, I mean, why should we introduce events that are not a part of the plant? I mean, the plant is the focus. We would like the plant to behave in a good way, in a specified way. And then it means that it's no meaning to add more events outside of what can be taken care of by the plant. So this is a natural assumption. But assuming this, we get an interesting result here, namely that when you look at the total specification, that is the alphabet of P synchronized SP. And then the definition of the synchronous composition is that you take the union of the alphabets of P and SP. So this is sigma P union sigma SP. But since sigma SP is a subset of sigma P, it means that the alphabet of the total specification is the same as the plant. And making this assumption simplifies the coming synthesis of the supervisors. So that's also a reason why we do this. Yeah, this is another example of just to illustrate what marked and forbidden states could mean. It's once again this A followed by B or C. And now the specification is that, okay, you should just take one B and then we are fine. Then you are in a goal state or in a mark state. While taking
have
C.
Have you changed your slide, Professor? Have you changed
Yes, I have, and it doesn't work.
No.
Okay, let's take it from the beginning again. Good that you remind me immediately. Yes, I should remember to say now I change new slide, and then you You will see.
Yes, I can see.
Yes, that's a good procedure. New slide. Okay, but now you see synchronous composition, including forbidden states, I hope.
Yes, yes.
Okay, then if you look at this is the same plant as we had used before. Now the specification is that just take 1B and you are in a goal state. But if you take C, you actually come to a forbidden state. What is then the synchronous composition of that system? So you could say that this is more or less a kind of training of the synchronous composition, but okay, it also has some small practical meaning. Since A is a local event, you easily get here, and then you can take B, and in the specification, you then get into a marked state, and since there are no marked states in the plant, both are actually assumed to be marked, and that means that this is a marked state in both the plant and the specification, and then you can take one more local A in the plant, and after that, nothing more can happen due to the specification, as can only execute 1B. And if you take the C direction instead, you immediately arrive into a forbidden state, and you can do one more A and get into another forbidden state. So once again, an illustration of the synchronous composition mainly, but also to see the difference between coming to a marked and a forbidden state. New slide. Now we define more clearly the two main topics we try to consider in our procedures here, and they are that we would like to have a closed loop system that is non-blocking and that is controllable. And then we will first use those concepts for verification, and then in the synthesis part, our goal is to synthesize a supervisor that is non-blocking and controllable. So that means that if a system is blocking, it's a bad behavior. If it's uncontrollable, it's also bad behavior. So those two must be avoided. So let's see how that works then, or how it's defined formally. I mentioned this non-blocking stuff a couple of times, but now I will illustrate it in more detail. And you could say that it's still more in text, but it illustrates more aspects of non-blocking than we had talked about before. So in this case, we assume that we have a total specification now, S0, which has this behavior. So here you don't see P and SP. They were something which generated this S0, which we see here. What can happen then? Well, we see here that if we go down on this road and on this path, and then you can arrive into the goal state or the marked state. And you can also go up here, and that's fine, you arrive into the marked state. But if you go into this state, Q1, either from the upper part or from the left part here, you see that if you continue to state Q2, that is a terminal state. You cannot do anything more. And since it's not a marked state, it's also a deadlock state. And a deadlock state is also a blocking state. Now, if you instead go to state Q3, you see that you can go to Q4 and back to Q3, but you will still go around here and will not be able to reach the goal state. Q2 is a deadlock state, while Q3 followed by Q4 and back is what we call a live lock state. Going back and forth, but nothing more will happen. And I would say that, you know, a computer typically don't run into a deadlock state, but a live lock state, because when you get serious problem with the computer, you see this something moving around on the screen, say some kind of waiting signal, and you cannot do anything more. It doesn't matter what you do, nothing more happened. And then you're typically in a live lock situation, and the only thing you can do is to totally reset or shut down and restart the computer. And of course, it's totally unsatisfactory to come into both these situations. And that means that actually all these 4 states, Q1, Q2, Q3, and Q4, are what we call blocking states, because from all 4, you cannot reach the marked state. All 4 are blocking state, but Q2 is a deadlock, and Q3, Q4 are live lock states. Q1 is a state from which you will only reach either a deadlock or a live lock situation. So the text you see here is more or less what I've seen. States where a loop is executed but without the possibility to reach a marked state. That's a live lock situation. Blocking state are all states from which a marked state cannot be reached. This includes both deadlock and live lock states. So a non-blocking system is simply, and that's a formal definition now. A non-blocking system is a system like this, if for every reachable state from the initial state via a string in the language of the automaton, from every state you can reach, it's possible to also reach to a marked state. It's always possible to reach at least one marked state in the set, among the set of the marked states. And that means that let's see here. Yeah, okay. You could say that first you go to any state in this automaton via the string S1. And then from this arbitrary state, you go from that state Q via a new string S2 to a marked state. And that is, so to say, a necessity to be able to do that. That string S2 must exist. And then both S1 and S2 belongs to the languages of the automaton. Well, this is the formal definition of this non-blocking procedure. Now the question is, how can we design a supervisor to satisfy this non-blocking procedure? And actually, I've already told you that. I did that. Okay, now we get some noise.
Yeah, Dr. Manbir.
Okay, now it disappeared.
Mute your mic.
Yeah, I muted. Sorry.
I forgot to tell you that I changed slide. You can see on the middle here the reachability algorithm.
Yeah, slide is done.
Yeah, fine. So now I will first show you the very basic first algorithm in the course. And that is a very, very general algorithm called reachability, and I've already illustrated that. When I take that in the backward direction, co-reachability, then we actually get the algorithm that can be used to generate the non-blocking procedure. So that's why I take this, present this right now. So let's look at this reachability algorithm. And the input to that algorithm is the set of events for the automaton, the transition function, the initial state, and if you have any forbidden states. Then we start an iteration and we say that Q0, the first set of states in your iteration, is the initial state set minus the forbidden states. Okay, this means that if the initial state is forbidden, you are totally lost. Of course, I mean, then you cannot even start this. So you could discuss if you should even consider that. But I mean, an algorithm should take care of all situations. So that's why we do this. Then you repeat k equal k plus 1. And here you can say that we have a breadth first search procedure. This is a breadth first search procedure, where you take the former set of states. The first one was Q0, the initial state. So Q0 union with all states Q prime that you obtain by taking a one-step transition where sigma of delta of Q, that Q belongs to the former set Qk minus 1, or the first time Q0, and sigma is an event in your alphabet, capital sigma. For all such states, target states, you can say from the source states in your current set Qk minus 1, you get a set of new states. And if you take the union of the former states and add the new state, you get the, so to say, new set of state Qk. And then you iterate this until you reach a situation where there are no more states to add. The iteration stops. And that is called formally a fixed point until Qk is equal Qk minus 1. And I guess that in computer science, you have talked a lot about these different types of fixed points. Many algorithms are just fixed points. And since we have a finite number of states, we assume that the number of states is finite. And that means that you know that this algorithm will also terminate. So a fixed point will really exist in this case, no question. And when you have reached the fixed point, you return this set Qk as the set of reachable states. And once again, this is a mathematical description of a breadth first search. Next slide. Yeah, here I changed from to an iPad, and the iPad has a very thin pen, so that's why it's a bit thin, the notations here, but I hope you can read it. Okay. I should just try to move the, so I can see here. We continue here on the verification part. I've shown you the reachability, and now I will introduce the co-reachability algorithm. And you could say that that is just that you go backward instead from the marked states. And then it could be relevant to say that, okay, if there are any forbidden marked states, they must be avoided. But otherwise, this is the starting point. And so you see also the co-reachability, instead of starting with have the initial state as the input, now you have instead the marked state as an input. And then you have a similar repetition here. And that is that in this case, instead you assume that Qk minus 1, that set includes a set of target states for this transition function. And then you would like to bring up any new source states to this transition. So if there is a state from which you can reach a state in Qk minus 1, that state is added to this set Qk minus 1. And then you add more and more, and once again until you reach a fixed point, and then you return Qk. Here you see that I take the set minus of on Qx all the time. Actually, I have to stop here again because doesn't work. Here you see that actually there is set minus qx missing here on this line in the first algorithm. It should be also written here, set minus qx. So now I'm back on the co-reachability algorithm, and what I will do now is that I will illustrate these two algorithms on the standard example I'm using in this part of the course. Namely this system.
So there is a question, Professor, by the Puja.
Yeah.
That can some set among a set of marked state be forbidden too?
Can some set among set of marked states be forbidden too? Yeah, I mean that's what I tried to illustrate by taking this operator. I mean, okay, you could say that it sounds a little bit strange that a marked state should also be a forbidden state, but assume that one engineer or one technician has so to say decided about the marked state, and another one has decided maybe later on that okay, the forbidden states are the following ones, and yeah, maybe the first person missed that. Okay, well, okay, sorry, some of the marked states I would like to achieve, they are actually also forbidden, so we have to take them away. So that is the motivation for, or a scenario where this could be motivated. So yes, there could be marked states that are still forbidden, but I mean normally it is not that. Thanks for the question. So now we apply the reachability algorithm, and here you will now see the perfect illustration of the breadth-first search. We start here in state 1, and then you go one step forward, and then you reach state 2 and 5. So that means that Q1 will be then Q0 union with 2 and 5, and you get 1, 2, 5. From these three states, you can reach then state 3 and state 6. So Q2 will then include both 1, 2, 3, and 5 and 6. And given this Q2, there are no more states to be added that can be added. So that means that Q3 is equal to Q2. And then I define this Q2 as the set of reachable states. Now the algorithm for the co-reachability works in a similar way, but then we start instead with the marked state, and you go backward. So then you have the states 2 and 5 together with 6, and then you go still one more step backward, and then you will also reach state 1, but also state 4. So 1, 2, 4, 5, 6, but not state 3 in that case. So those states, and then you have the fixed point, and those states Q2 are also then called QC, and they are the co-reachable states. The trim automaton includes the states that are both reachable and co-reachable. So then we take the intersection of QR and QC, and then you get 1, 2, 5, and 6. And this is actually the non-blocking supervisor. So if you take the co-reachability algorithm on any type of total specification, S0, then you get actually a non-blocking supervisor. But to also reduce that if there happen to be any unreachable states, so then you can just clean up the automaton, and then you make also forward reachability. It's not necessary to get the functional system, but to save memory, you could say it's good to also take that step. Now it's really problematic here because it stops all the time.
Do you use new share from the green button instead of?
I used the green share screen but then after some time it blocks, and I know that problem since many times, but it doesn't used to be like this. If it works, my experience if it works when I start, then it will continue to work. But here, no, it does not work at all. So then we have to do like this instead. I have to skip the full view, because then if I show it in the screen mode, then it used to work. Or let's see here now what happened. Now share screen again. Yeah, we have to do like this instead. So I cannot use the full screen mode, but you can see it in any case.
Yeah.
Okay, so then you have seen this, and now I don't think I will need to ask you about this if you see or not, because now I will be quite sure that you will see my switches. But okay, you have to tell me if that's still a problem, but I think that now it will work. So then the question is, what can we do with verification based on this reachability analysis? And you could say that what I show you here is not very advanced, but still it's the typical procedures that are used in computer science related to what is called model checking. But there is one thing still missing compared to complete model checking, and that is that the specifications in model checking or formal verification are typically given by temporal logic. And when I have completed this presentation on synthesis and verification based on automata, I will also tell you more about temporal logic, but that comes after this part. If you look in detail on the schedule, you could see that the official schedule is a little bit different, but I found it better to take this order. So I present the automata version of this, and then I add with temporal logic after that. And then you can say that what people do is typically that they specify a temporal logic expression as a specification, and then ask, is this specification satisfied by the given automaton or a finite state machine? Now, in this case, I instead give the specification in terms of an automaton. And to be honest, my feeling is that, okay, yes, temporal logic, it has been very popular also in my area on discrete event systems more recently. But and it looks nice sometimes with the temporal logic expressions, because in some cases you can get very short descriptions and so on. But at the same time, it's sometimes a bit unclear what you would really achieve with this, what these temporal logic expressions mean. So my feeling right now is that a simple automaton, which we quite often can generate, and when you have got some experience, so to say, on automata, then I find that equally useful and sometimes even better than the temporal logic. But they are complementary. I can just tell you a short story. When I started this in this field, I had a guest researcher in our department. We met at a conference, I think it was 1992 or so. So it's quite many years ago, 30 years ago, yes. And then, yeah, it was not so easy to understand all these automata. And I remember I was sitting with this guy, and he tried to explain to me about some small automata, and I couldn't really understand what he was talking about. And after some time after that, I realized, oh, okay, how stupid I was. I mean, I couldn't follow his discussion. And I hope that you are not so bad as I was at that moment. But it indicates also that, yes, there is, as with all languages, with all expressions, all modeling features, it is a threshold before you really understand it. But when you have got the feeling, then it's often quite easy to get an understanding. And right now, my feeling is that automata, although some people are skeptical on that, they are actually quite useful and understandable. Although you could say that my examples here are very simple. Yes, they are. But now I will show you what we can do with verification then. So the first question we can ask is generally, is a specific state reachable? For instance, is a marked state reachable? Or is even, it's not necessary to talk only about one specific state. You could also talk about a set of states. But in this case, we could ask simply, is this state reachable? And then, of course, it's just to see is when you have computed the reachable states, is this specific state a member of the reachable states, or even a set of states? Is that a subset of the reachable states? Yes, then you get answer yes or no. More interesting is maybe if you have a set of undesirable states, forbidden states. And then you could simply ask, is the intersection between the reachable states and the forbidden states empty? And then it's good. If it's not empty, then there are reachable forbidden states, which are, of course, unsatisfactory. And this second topic is actually the most common problem that is considered within model checking and formal verification, the safety analysis. And you could say that this step 2 is just safety analysis. And as I mentioned, the first lesson, this safety problem, there are some fantastic algorithm, and especially one called IC3 that was developed by a guy called Bradley, say, I think his first formulation was like 15 years ago. And it was soon realized, oh, this is really a breakthrough. This is something that is much better than we have seen before. And he used some special tricks, and it was actually quite hard to understand what he had formulated. So even I think his first paper was not accepted because the reviewers didn't understand what he was talking about. But after some time, some other people realized, oh, this is a wonderful result. So they supported him to publish his results. And now this IC3 is, I think it's considered still as the best algorithm, or let's say at least one of the absolute top algorithm. You could say that it's not one algorithm that is best for every problem, but the thing was that this algorithm was very good on many standard problems. What I did just 2 months ago, or say 1.5 months ago, was that I tested our procedure in Supremica and compare that with this IC3 algorithm. The IC3 algorithm you can use from this tool new XMV, which I mentioned about the first lecture. And as I also said there, so sorry, this is a repetition, but I give some more background to it now. Our algorithm then was definitely competitive, and quite often it was actually better than what I consider as the best algorithm. So I realized that we have to make some publications of these results. Okay, so that was about safety analysis and about forbidden states. Actually, our algorithm has not been mainly developed for safety analysis. It's actually an interesting tool for non-blocking problems, including even these uncontrollable events, which I will talk about later today. So then we had the third problem here, and it's more a dynamic problem, we can say. The first two are in some sense more static. I mean, you have a set of states. What is the property of these states? Is a state reachable, or is it not reachable if it's a safety problem? The third one is that if you have a sequence of event or event sequences given by specification, is this behavior possible in an automaton? And that could mean that okay, is it possible for this system to go from state, like this specification? Is this repeated loop behavior, B, C, B, C, is that possible in my system? What you can do then is that you take your automata, which you would like to analyze, and you synchronize that with your specification. And then if that result is non-blocking, then it means that the specification is a part of the behavior of A. While if A synchronized with SP is blocking, then the SP event sequence is not possible. So let's illustrate this. So here we have A followed by B or C, the standard example in as the model. And then if we have the specification B followed by C, we can immediately see in our model here, yes, B, and next time C, next time B, and C again. That repetition works fine. It's exactly what I showed in the beginning of this lecture. So SP is a possible behavior in A. Now, let's see here, if we look at the following specification, B. If I say A, B, C, and then back A, B, C, is that possible? You could maybe really already here see, because the model is A is quite simple, but I mean, you see you can make A, B, and what happens then after that? Yeah, okay, let's look at the synchronous composition here. Then both can make an A, and you are in the two state. You can also make a B, and then you are back in the one state in the planned A, and you are in state 3 in the specification. But after that, you cannot do anything more, because the specifications say that the next event must be a C, while what A can do is only A. So in this case, you have a blocking state here. You cannot reach back to the marked state. So that it's not possible to execute this sequence in your original system. So this was more a kind of dynamic specification asking, is this sequence possible or not? Now I would like to look at the second problem. You were first talking about non-blocking, and now it's time for this controllability problem. And I'm just looking at the watch here and see when we should take a break. But let's say that we go on with 20 more minutes before we take a break. Or maybe a quarter. Controllability. We have still the plant, we have our supervisor, and we have now also the assumption that the supervisor is a subset of the plant. Remember that even the first candidate of a supervisor had this property, which we also call the total specification. The closed loop system is P synchronized S. And now we make an interesting assumption here, namely that the plant alphabet is divided into the set of controllable and uncontrollable. So this dot above means that the intersection between the two is empty. So there are no shared elements in C and U. Either an event is controllable or uncontrollable. Sigma C is the set of controllable events which the supervisor can accept or prevent, while sigma U is a set of uncontrollable events which S cannot prevent. So the meaning of this is that if a controllable event, if an event is controllable, the supervisor can say, no, you are not allowed to do this. And actually, the supervisor should always, the plant should normally ask the supervisor about the controllable events, if they are acceptable or not by the supervisor. On the other hand, the uncontrollable events, they are events that the controller cannot prohibit. They just happen spontaneously. And there are two typical examples on this. And the first one is the user interface. You could say that, say, a coffee machine or something, the controller, the system, must always be responsible to the fact that the user can push any button on the coffee machine. Otherwise, it would not work. So this is an example of an uncontrollable event which the supervisor within the coffee machine cannot prohibit. It must always be ready to accept any user interface action. This is, in my view, right now, the perfect application of uncontrollable events. The other typical application is, in some sense, the more obvious one, which you always have, namely, even if you don't have any user actions, you always have sensor signals or sensor actions, sensor events. And those are events that, the sensor just give a signal. It don't care if the controller of the supervisor asked for it or not. It just sends an event when something has happened. So, a sensor could just be a light signal, to take a very simple example. And when the light starts, the event has happened. The light started, and that's something you cannot prohibit. So sensor signals and user actions are the two most typical examples. But it could all of uncontrollable events, but it could also be, for instance, a modeling feature that you say that, okay, well, when a machine has completed its work, it does not ask the supervisor to stop them, if it could stop or not. Even it will automatically expect that there is a place in the output buffer of the machine. So that means that when a production starts in a machine, or a task starts in the machine, the buffer, the output buffer of that machine must be empty, because the machine can at any time put its piece in that output buffer. And that is then modeled as the, so to say, completed event. The complete event in the machine is uncontrollable. And this is also a classical example in the literature on uncontrollable events. I would say that it's not, in my view, the really perfect example, because, I mean, why should a machine always expect that the output buffer is empty? Of course, the part could wait in the machine until the output buffer becomes empty. That is a more natural assumption. But just to illustrate what uncontrollability could mean, this is another example. I would like to give you the opportunity to give comments or questions on this, because this is very fundamental. And is this clear for you now, what I mean by an uncontrollable event and a controllable event? No response? It means
you can write yes.
Oh, let's
no,
see. There is one thing in the chat.
Okay.
No, okay, it was an old one. Yeah, okay.
So please write yes or no if you have not understood, or yes, please. They would will be.
Yeah. Okay.
Anybody who's.
It seems like it's okay. I will take a look at it.
Okay. Okay.
At least I hope that you follow me now. Something, sorry, that you know, I forgot to mention before when I looked at this, I presented this reachability algorithm. You should answer a quiz here on Saturday, and I mean, an example of a question in the quiz could be that you generate, for instance, the reachable or co-reachable states and show how the algorithm works for that. So that could be a simple illustration, just to help you. I mean, we would like you to just be able to follow and understand the course, but this could be a simple example of a quiz question. Controllable supervisor, what does that mean? Yeah, now it's critical that the supervisor is always able to follow the plant. And that means that if the plant spontaneously executes an uncontrollable event, then the supervisor must also be able to follow that. Otherwise, they will get out of synchronization, as we sometimes say. And that means simply that we assume that P synchronous S, the synchronization of the plant and the supervisor, always works. We assume that this is a model of the closed loop system. But if the plant can make an event which the supervisor cannot make, and if that event is uncontrollable, the plant don't care about if the supervisor can follow it or not. So that means that this model does not work. It's not correct in that situation. So simply, we would like to generate a supervisor now, which is controllable, meaning that if the plant makes an uncontrollable event, the supervisor will always be possible to follow that. That means that if it's an event that is local in the plant, it's not a part of the supervisor, then it's fine, because the synchronous composition says that, okay, the plant can make any local event and they are still synchronized. But if it's a shared event between P and S, an event that is including both P and S, then that event must be able to be executed by both P and S. So that is the critical point. And for those shared events, the supervisor must be able to execute also uncontrollable events. And that is exactly what we mean by controllability. So we say here that controllability is related to the uncontrollable events in P that are also part of the supervisor alphabet. And that's the situation where you have a shared uncontrollable event. So a sigma u that is both in the supervisor and also an uncontrollable events. Those are the critical ones. Then the definition of controllability is as follows. A supervisor S is controllable with respect to the plant and a set of uncontrollable events, which is a part of the plant alphabet. If for all reachable states, P, Q, in the set of reachable states for the synchronous composition P synchronized S in the closed loop system, P synchronized S. And for all uncontrollable events in which are both in the supervisor and in the set of uncontrollable events. It's for those we have a specific property here. So this was a long background to the specific mathematical expression here, saying that, okay, if there is a transition from this specific state P in which is also a reachable state in the synchronized system. So we said that a reachable state in the synchronized system, P synchronized S, has a plant part P and a specification part, supervisor part Q. Okay, from that state in the plant, if you have an uncontrollable event, an uncontrollable transition, which is also possible in the plant, you must also have a corresponding transition in the supervisor. So then there must also be a transition from Q via the same uncontrollable event. And the result of that transition, the target state of that transition, must also be a part of the supervisor state. So this means that S must be able to follow P when P executes an uncontrollable event in sigma U intersected with sigma S in the closed loop system. So now I will illustrate this very easily. In this case, now I assume that D is an uncontrollable event in the plant. So that means when the plant goes to state 2, it can either take the controllable event or the uncontrollable D event. So sigma U includes the event D, and we also put this explanation mark before D as a notation for that. You see that there is another uncontrollable event here, which we will see soon is not critical, but you could have uncontrollable events, so to say, everywhere in the plant. Now I have the following supervisor. Well, it's actually the same as the plant, except that we don't include this uncontrollable transition to the state 3. Now we take the synchronous composition of P and S. What do we get then? Well, we get 1, 1, 2, 2, and 4, 3, and 5, 4. It means that P synchronized S is actually structurally the same as S, but if we look in detail, we see that the state names are not the same. But we don't care about that. We say that, well, they are isomorphically equal. Now, since D is uncontrollable, and when we have reached the state 2, 2, it means that state in P and that state in S. Then the plant can make an uncontrollable D, which the supervisor cannot. That means that this is an uncontrollable state, where the supervisor cannot execute D, which P is able to do. And this is a dangerous situation, because if the plant P is doing that, the supervisor has no meaning, has no idea anymore where the plant is, because the supervisor said, okay, we should make a B. But when the plant has reached this state 3, no B can happen. So you could say that this state 3 has two problems in some sense. Well, okay, actually here, you see, I don't have any marked state now. And the controllability has nothing to do with non-blocking in itself. That means that marked states have no meaning. So we could say that although we had before that this state 5 was a marked, it was a marked state. And so in that sense, it was state 3 was also a blocking state. But now it's not a blocking state anymore, because we don't have any markings. We don't have any marked states here. So no question about non-blocking. In this case, it's just that the plant can do something which the supervisor is not able to do. So in that case, this 2,2 is a bad state. We must avoid that. Still, it's okay, because we can take this alternative road. And then the supervisor says, let's take a C followed by an uncontrollable D. And then you could say that the plant first make the controllable C, and then it don't care to ask the supervisor. It just spontaneously take the uncontrollable D. And we are still fine, because we have together reached this state 5,4. So in this sense, we have now an uncontrollable states, and they are defined as follows. The uncontrollable states are states in the synchronous composition such that if there exists an uncontrollable event, which is also a part of the supervisor, and there is a transition from P via an uncontrollable event, and such a transition exists, while that transition does not exist in the supervisor. The corresponding transition with a state Q in the supervisor via the same uncontrollable event, that does not exist. In that case, you have an uncontrollable state. So you could say that, well, here is in principle the algorithm to detect if we have a problem with uncontrollable events or uncontrollability, meaning that we try to identify all uncontrollable states, and those must be taken away. And when you have taken away the uncontrollable states, you could actually have generated some blocking states. So then you have to also take away the blocking states, and then there is a risk that you have generated new uncontrollable states, and then you have iterate this loop once again till you reach a fixed point where you can find that, okay, all states are now both controllable and non-blocking, and then you have reached what we called the perfect supervisor, or the controllable and non-blocking supervisor. I think we take a 5 minutes break there before we go on, because what I will do now is after this to go through some more detailed peculiarities in automata, which we need to really define what we mean by equality and so on. But we do that after this 5 minutes break. And you can ask questions also during the break via the chat.
Yes, please.
Thank you. So let's, for simplicity, say that we start 11:45. 11:45. Yeah, then we say we can start again.
Yes, please, we can start.
You start the recording.
Yeah.
So then we will continue with this supervisor synthesis, because what I actually showed you before was more the definitions of controllability and non-blocking, and I showed you one very, very simple example of the verification problem here, how we can handle that. And now we will go on with the synthesis part. Now we will extend our plant, including both the subplant P1, P2 until Pn. So this is actually the typical situation where a plant, a system, has a number of components that are synchronized together. So together they constitute the plant. And for instance, when I mentioned about this locking alarm system with its 1 billion states, of course, it was not one model itself that generated that billion states. It was a combination of a number of small software programs and also physical behavior, which was modeled in this way. In the same way, we can also have a number of local specifications. First, the second one until specification SPM. And all these together synchronized generate the total local specification. It's still not the total specification, which we said was P synchronized SP, but that comes on this next line. The total specification is then P synchronized SP, and a peculiarity here is that it doesn't matter in which order you take these synchronous compositions. You can start wherever you like. You can first take, for instance, Pn synchronized with SP1, if you like. And then you can synchronize with SPM and then P1. It's like addition. You can take the addition in or multiplication in any order. It means that the operation is associative and also commutative. Okay, if this S0, the total specification, has any blocking or uncontrollable states, such states need to be removed to get the controllable and non-blocking supervisor. And then this supervisor is, well, you cannot say that it's a subset, because a subset is defined for sets, and the supervisor is rather a tuple of a number of different sets. So the question is, what does it mean that S is something less than S0? Well, we say that that it's a subautomaton of S0. S is a subautomaton of S0. This supervisor S is also a model of the closed loop system when the supervisor alphabet is a subset of the plant alphabet. So S is equal P synchronized with S. Okay, now I've used two operators here, equality and this less or equal. Less or equal related to automata. I mean, it's easy to understand what less or equal means for real numbers. 5 is less than 6. But what does subautomaton of or less or equal means for automata? And what does equality means for systems where S has one set of states and P synchronized S is actually cross product between different with the states in S and P. So clearly we have some problems here. We need simply to define what we mean by a subautomaton and equality. And actually equality, I have already talked about this isomorphism, but I will now try to define that a little bit more in detail. Okay, just a reminder here that the closed loop system is this type of system where we have the closed loop model is the synchronous composition between P and S. So first the subautomaton then. So once again, we assume now I take two arbitrary automata. So A and B, there is no specific saying that, okay, A is the plant and B is the specification, just two basic automata. In this case, both also include marked states. Then we say that A is a subautomaton of B written A less or equal B. If the set of states in A is a subset of the set of states in B, we assume that the alphabet of A and B are equal. That could be considered as a kind of restriction, but it's a part of the definition to make things a little bit more easy to handle. It could, of course, be generalized, saying that, for instance, sigma A is a subset of sigma B, but then you get into more detailed complications, which are actually not necessary for our purposes here. So we assume that the alphabets are equal. The transition function is a subset of A is a subset of the transition function of B. Well, that means simply that you have less transition. All the transitions in A are also part of transitions in B. So this is actually more easy to understand if you consider the corresponding transition relations, because they are pure sets. Here, when you have functions, it's a bit more complicated. But the intuitive meaning of this is that the transitions in A are also involved in B. The initial states are the same, and the marked states in A is a subset of the marked states in B. Well, this sounds reasonable. It's something that simply is less than something structurally less in A than B. And actually we can see here that we have a simple example of a subautomaton A related to another automaton B. Well, there is one difference, and that is that the state names are somewhat different. But we don't care about that at the moment. Otherwise, we can say that the structure you have in B, you can also find in A in terms of states and transitions. Here you go from one state via transition with event A to a target transition, and you have the corresponding transition in B, and the same for the second transition. Then B has something more. It has another event, but okay, we said that we should have the same alphabet. That means that the event C is also assumed to be a part of the alphabet of the automaton A, but that's fine. It just means that we say that the event C is not allowed in A, so there does not exist a transition with that label. But now we would like to generalize this to also take care of the fact that they have different state names. And the specific situation we consider here is that typically B is a synchronous composition of two automata, and then you get different combinations here at least 2 elements here instead of here only 1 element, 1 state name here, and here you have 2 state names, 0, 1. It's a state 0 in one automaton and it's state 1 in another automaton. But now we can make a functional mapping from all states in state names in A to B. And that functional mapping is isomorphic. Or you can say it's a one-to-one mapping. And if that is the case, you could say that you satisfy the fact that, okay, yes, they could have different names, but it doesn't matter. There is always a one-to-one mapping or a bijective function such that every state in B is a function, a unique function of a state in A. And if that is satisfied, we call that you have an isomorphic mapping. So in that sense, we have identified what a subautomaton is. Then we also need to look at what does equality means, or an equivalence between 2 automata. And the first simple equivalence is that of language equivalence. That means simply that 2 automaton are said to be the same, or they are equivalent if if they generate the same language. And that includes both the complete language and the marked language. The marked language only includes the strings from the initial to the marked states, while the complete language includes strings from initial state to any state. So language equivalence, then it's enough that the strings coincide with each other. But structural equivalence is a bit harder, because it said that if A is a subautomaton of B and B is a subautomaton of A, then they are equal. And this equality, which you see here, I call it here structural equivalence. It was actually something formulated by my first PhD student, but I think he got that from a very old and basic advanced book on automata theory. So it was, of course, not his own formulation. But nowadays, when I look at the literature, they typically say, well, okay, this means that the 2 automata are isomorphic. So now we can look at a couple of examples and see here that, for instance, A and C, they are both language equivalent because they generate the same language A followed by B. The strings are A and AB, and the marked string is AB, and it's the same for C. So they are language equivalent. But they are also isomorphic. They don't have the state names, but they have the same structure, the same transitions. And there is a clear mapping from 0 to 2, from 1 to 3, 2 to 4, a one-to-one mapping of the state names. We see also that A is a subautomaton of B. But how is it then with D? Well, here we could say that the same D and B, they have the same language because they generate A, AB, and AC. On the other hand, they are not structurally equivalent because in the B automaton, you separate two marked states, while in D you have one marked state. So with the B and C event, you reach to the same target state. So then we could say that B and D are language equivalent, but not structurally equivalent. Then there is another notion which is called refinement. And that simply means that if A refines P, it means that A synchronized with B is equal to A. And you could say that this is just structural information. It means typically that A includes some more details than B. But on the other hand, also, if A is a sub-automaton of B, it implies that A also refines B. But the opposite, refinement does not guarantee that A is a subautomaton. So if you have this property satisfied, it does not guarantee that A is a subautomaton of B. So it's only an implication, it's not an equivalence in that case. Okay, B refined. Yeah, okay, this is interesting. B refines D since B synchronized with D generates this, and that means that B and B synchronized D are isomorphic. They are equal. And that means that actually what I said before here was correct, but I was not totally sure. I was a bit uncertain myself here. Because what I said was that now we took B synchronized D. B includes some more details compared to D, because in the final states here, the goal states, they are separated. So you could say that B has a kind of more rich behavior than D, where in D you don't care if after the B and C they join one common state. While in B you say that, okay, if you're taking B, you go to one state, and with C you go to another state. So in that sense, B has more details than D. It means that B refines D. And I think from a language point of view, refinement has its meaning then. Now I will present, I think, the only lemma or we're including a formal proof in this course. It's not very much on proof aspects here, but here is a simple proof also where we will apply some of these rules we have now shown. So if a supervisor S is constructed such that S is a subautomaton of the total specification S0, that means that S is subautomaton of S0. Then S refines P, meaning that P synchronized S is equal to S. That means that the supervisor is also a model of the closed loop system. Okay, what kind of meaning does this mean? Or why is this important? Well, it's actually quite interesting, because what is said here is that if you start with the total specification, and then if you make a synthesis of a supervisor, meaning that you take away some states from the supervisor, meaning that S is a subautomaton of S0. Then you also know that still S is a model of the closed loop system. So even if you take away some states from this P synchronized SP, the total specification, you know that the supervisor still is a model of the closed loop system. Yeah, I mean, it could be discussed if this is important or not, but yes, it is important because it means that the properties you generate for S, for instance, that S is controllable and non-blocking. It also means that the closed loop system is controllable and non-blocking. So this is a wonderful result. So this means that we start with S0, the total specification, and then we remove some bad states, the uncontrollable states, and the blocking states. And based on that, we get a supervisor which has good properties. We know that the supervisor in itself is non-blocking and controllable. But that also means that the closed loop system, when you apply this supervisor together with a plant, then that total system is also controllable and non-blocking. Okay, how can we prove this? Well, first we said that, okay, we had the assumption that S is a subautomaton of S0. S is less or equal S0, if we like. But we also said that this implies that S refines S0. It was that A less or equal B means that A synchronized B is equal A. S is less or equal S0. It means that S is equal S0 synchronized S. So S refines S0. Now we also know that S0 is P synchronized SP, like this. Now we make a simple calculation here. Now we start with S0 synchronized with P, and S0 was P synchronized SP. So I now replace S0 with what it is, namely P synchronized SP, synchronized with P. Now, I said before that when you have synchronous composition, you can take this in any order. So instead of first making P synchronized S, taking P synchronized SP, I take actually, you could say I skip the parenthesis here and put instead the parenthesis around P synchronized P, and that means that I have also moved. Yeah, okay, sorry, now I see here. First, I use the commutative rule here that I can take like A synchronized B is equal B synchronized A. The order between the two elements in the synchronization can be changed. That is what I do here. And then I use the associative property, meaning that I take first P synchronized P, and after that synchronization with SP. Well, okay, you could think that I'm too detailed here, but actually it's critical. It's not absolutely at all obvious that you can do this, but the synchronous composition as it is defined, has these two properties, that it's commutative and also you can take the synchronization in any order. Now it happens that P synchronized P is equal to P. Once again, it's on the isomorphic level, because P synchronized P has two state names, but they are from its, if you have a state name, say Q in P synchronized P, the corresponding state name will be Q comma Q. But we say that they are equal, and because they are isomorphic. So P synchronized P can be replaced by P, and P synchronized SP was equal to S0, as up here. So now what I've shown is that S0 refines P. S0 is equal to S0 synchronized P. S refines P. Now you have this transitive property that, okay, since also S refines S0 and S refines S0 refines P, that means that also S refines P. So you have first S refines P. S is a subset of S0. S0 is not a subset of P, but S0 refines P. And that means that S also refines P. And therefore, S is equal P synchronized S. So you could say that this transitive property could also be proved by looking at these synchronous composition a little bit more back and forth. But I have just written this in text now. Okay, so by this, I have actually shown exactly that if you assume that S0 is P synchronized SP, which also means that S is now, okay, sorry. S is a subautomaton of S0. Then S refines P, which I explained earlier, which is actually very important, because it's enough for me to manipulate the supervisor, and I know by that I still have the guarantees property of the closed-loop system. So now I will go on with the controllability aspects of the supervisor, because there are still some more problems related to that, especially when we make the synthesis. So now I assume again that the plant alphabet can be divided into a controllable and uncontrollable part. What we do first is that we try to identify all the uncontrollable states. You know what we did up here. Here we identified that, well, this was an uncontrollable state in the synchronous composition, and that means that we have to remove that. We have to consider that as a forbidden state. So the first thing is that we look at this S0, P synchronized SP, and see, are there any uncontrollable states in that system? Then we consider those states also to be forbidden. So we include them in the set of forbidden state QX. Now we have actually a combination of forbidden states You can also have, you can also have explicitly forbidden states, both in the plant and in the specification. Okay, they are here. Those are what we call the explicitly forbidden states. Like, you know, I said that the state where two robots are in the same zone is a practical example of a forbidden state. That state would then be a part of this explicitly forbidden states in S0. But to that, you also add the uncontrollable states in p-synchronized SP. So all states in p-synchronized SP which are uncontrollable, they are also now included in the set of forbidden states. Okay, I had this example before, and it's just repeated again that we find this to be an uncontrollable state. And that means that the supervisor is then state 1,1 followed by C and then the uncontrollable D. This is now a controllable supervisor. But more things can happen. So we need to extend this uncontrollable state aspect. Now assume instead that you have a plant like this. You see, compared to the model I've used before, I also include here one transition from state 3 to state 6 and one additional state 4 here. Now I say that, well, the specification I have here, note that so far I haven't introduced any marked states. But I say that I don't want to go to that state 4. So that's my specification. I skip the possibility to go to that state 4. Then I synchronize P and SP. And you see that it's more or less the same states in P and SP, except that we skip that state. But you also see that you have 1, 1, 2, 2, 3, 3, but then you have 5, 4, and 6, 5 as the states. In this case, I introduce now the notation of US equal to an uncontrollable state. Okay, why is 3,3 an uncontrollable state? Well, it's easy to see that, because if you look at the specification and the plant, and when they both have reached the state 3,3, then the plant can make an uncontrollable transition, which the specification cannot. So that means that 3,3 is from the beginning an uncontrollable state. But now, when we remove that state, if we now look at this system, then we find that, well, if you compare this model now back again with the plant, then we see that the plant can also make an uncontrollable transition from 2 to 3, but we have forbidden the state 3 also. So actually 2,2 is also an uncontrollable state. Now I did a comparison with the plant to find this. But actually that is not necessary. By just starting from the forbidden states and going backward, as long as you have uncontrollable transitions, then you get what we call the extended uncontrollable states. So first we identified comparing the plant with the specification that, okay, this is an uncontrollable state. From this, we now go backward with the uncontrollable states, uncontrollable events. And then we also find that this is uncontrollable because from this state, there is an uncontrollable transition to another uncontrollable states. Maybe I repeat myself here. From this state, there is an uncontrollable transition, a transition with an uncontrollable event to a forbidden state. That means that this must also be forbidden. So that is what we mean by extended. If there is an uncontrollable transition to another uncontrollable state, the source state in that transition must also be forbidden. So that's why this is called the extended uncontrollable state. And you could say that this is forbidden. Sometimes I call that US0 because it's forbidden from the beginning. Just identifying the uncontrollable states. Then in an iteration, in the first iteration, then this is found also to be extended uncontrollable, and then I call that a US1 state in the first iteration of a procedure, which I will show you some. So the controllable supervisor is also in this case, for this more complex situation, it's also only go in this direction. Take event C followed by an uncontrollable D. So state 2,2 is an extended uncontrollable state, since an uncontrollable state in S0 can be reached by an uncontrollable transition in S0. But the good thing here was that I don't need to consider the plant anymore. It's enough that I go for this S0 and I have first identified the uncontrollable states, the originally uncontrollable states, and then I can just stay with S0 and make manipulations of that. And in the end, I get something I call S. And because S is now a refinement of S0, I just removed some parts. I know that this is also a model of P synchronized S. That is, S is equal to P synchronized S. That was an application of this lemma 7.1. Extended uncontrollable states are avoided by going backward from the uncontrollable states as long as there are uncontrollable transitions. So these states are then also forbidden, and they are actually computed by a co-reachability function, or a co-reachable algorithm. In that case, I start, instead of starting with the standard co-reachability algorithm, we started with the marked states. Then now we start instead with the forbidden states in S0 and go backward with only uncontrollable events, uncontrollable transitions. So the alphabet is not the whole S0 alphabet, is only the uncontrollable alphabet. And so to say, the starting point is the forbidden states in S0, which now takes the place as the marked states in the co-reachability algorithm. And that means that the originally forbidden states in the co-reachable algorithm has no meaning here. So we put an empty state there. So just to show you what will happen applying that algorithm, it means that this is the first QXS0 state, and then you go backward with an uncontrollable event, and you also reach that. After that, nothing more will happen, because this is a controllable event, this is a going backward, this is a controllable event, and those are not included in the alphabet. So that backward transition will not be involved. It will not be generated because the alphabet only included the uncontrollable event in that case. So by this, we have generated the extended forbidden states. And what I will generate now is actually a theorem. I will not include any proof of this because the proof looks quite strange. But let us read at least the theorem. Given a plant P and a total specification P synchronized SP, there exists a non-blocking and controllable supervisor S such that the closed loop system is a subset of P synchronized SP. If and only if there exists a non-blocking and controllable supervisor S prime, which is a subset of S0 equal P synchronized SP. And what this theorem says is that, okay, it's enough for me to generate a sub-automaton of S0. And then I know that this is also a controllable and non-blocking supervisor for the closed loop system P synchronized S. And that, you could say, was more or less what I said in lemma 7.1. So it's a very simple reformulation, you could say, of lemma 7.1. So the algorithm which we will look at now is the following. I used to formulate this as I said, this is the crown of this course, because here we generate the perfect supervisor. We synthesize the perfect supervisor, and actually it has even more good properties than I have talked about explicitly here. I will come back to that soon, and it's about what is called an optimality condition. But let me come back to that. First, this algorithm 3, the first algorithm was reachability.
Hello?
And, yeah? Is it any problem?
I don't know if my network is down, or your, I mean, we are not able to hear, I'm not able to hear your voice. Are you able to participate?
Yes, ma'am. The voice is clear. I think there is some issue in your side.
Okay.
No issue.
Aparajita, you don't hear me?
Breaking? Yeah, or
Ma'am, your voice is breaking.
hello?
Hello?
My voice is breaking. Okay, fine.
Yes.
So it's a fault from my side. No issues. Then please go ahead, please.
Okay.
I'm so sorry. I thought that there's something wrong. Yeah.
So as I tried to say, I consider this as the most important result in some sense in this course, because what I will show you by this algorithm is now that we are able to synthesize the best possible supervisor that avoid any non-blocking states, and it also takes care of the uncontrollability problems. Before I show you this, go through this algorithm, I would like also to mention that in computer science, there is a technique or a procedure called game theory. And game theory has its background in optimization, where, so to say, you have two players that are fighting against each other. there is a very famous result by Nash, who formulated this original game optimality, and it's actually a saddle point in an optimization criterion. But in this case, you could say that game theory for discrete systems, which we're talking about now, has a little bit different flavor, but it's still a fight between the good and the bad guy, and the bad guy in game theory, in our case, is actually the environment, and what we need to synthesize a procedure, a controller, which will not be where the environment tries to sort of say make things bad, and that should be avoided. And actually, what is bad in this case is that the plant can make these uncontrollable events, or the environment. For instance, this user can play around with these push buttons, and the supervisor must be able to handle that. So in computer science, the formulation I have given you here, it's formulated typically as a game problem. And in that case, you could consider the uncontrollable events as the environment trying to create problems, so to say, and then to be the winner of this game, the supervisor must be able to follow all these environmental steps or actions, and still be able to reach the goal states of the system. So in our field now, we have tried to relate to this. The field in computer science is called reactive systems, and there they are typically formulating these game problems. And in our field, the background I have with more of control background, then we talk about the uncontrollable events instead of formulating this game formulation. But actually, we are more or less solving the same problem. So now to the details here. I call this algorithm safe state synthesis. It's safe in the sense that all uncontrollable states are avoided and all blocking states are avoided. And I assume that you as a specifier or as a user has both given a model of the plant with its controllable and uncontrollable events, and you have also said what kind of behavior you would like to have by these local specifications, SP. So the first thing you do is that you generate this first candidate S0, and based on that, which was p-synchronized SP, that S0 is the input to this algorithm. So if you like it, we could even have, that is actually what is written down here, that, okay, you apply this algorithm for S0, and the algorithm here will then generate a sub-automaton of this S0. So you call this function by Q S0, sigma S0, sigma U S0, delta S0, QM S0, and QX S0. So all the states in S0, the first candidate, all the events, but also specifically the uncontrollable events in S0, the transition function, any marked states, and of course also any forbidden states. Then we start our iteration by saying that X0 is the forbidden states. So you could say that we will iterate on this X. And so XK is generally forbidden states. And we start with those that are forbidden from the beginning in your specification. And what this algorithm will do is that it will extend this set X0 with more forbidden states. And those are the blocking states and the extended forbidden states. So now we have an iteration here, which we repeat until we reach a fixed point on the forbidden states. And then we return Q set minus the forbidden states, all the states minus the forbidden states. Now this routine here in the loop includes actually two calls of the co-reachability function. The first one is to generate the non-blocking states. And then what we do is that we take the co-reachability function with the event set, the transition function, the marked states as input, and any forbidden states. And this was, so to say, the old forbidden states. Then we start with going backward from the marked states, taking into account any forbidden states, going backward until we have reached the fixed point here. And then we know that we have all non-blocking states, because that's exactly what is achieved by the co-reachable function. Well, there could be now generated some unreachable states, non-reachable states. But at the moment, I don't care about them, because I say that, okay, in the end, the result here, we could also make a forward reachability to make the automaton, the state space trim. But it's actually not necessary. It's more to save space in the computer. Then we note that all states which are not non-blocking, they are blocking and forbidden. So Q set minus the good non-blocking states, they are now the, so to say, new forbidden states. Okay, from those forbidden states, we look at the extended forbidden state due to uncontrollable transitions. So then we go backward from these forbidden states with our transition function, but only taking into account the uncontrollable events. Then you will actually extend the set of forbidden states. So then you will update XK again, including also some extended, if there are any extended uncontrollable states or extended forbidden states, if you like. Now the problem is that when you have done that, here you know that Q set minus XQ generate a controllable state. A controllable state set, yes. But this second operation could have generated some new blocking states. So now we need to go back and look at, have we generated some new non-blocking, some new blocking states, sorry. And then you repeat this until you have reached the fixed point, until you don't remove any states anymore. And by that, we know that taking away all the forbidden states from Q, you have reached a state set, QX, in the supervisor, which guarantees that you have non-blocking and controllable state set. I also said that it had some other nice property, namely an optimality property. And that is simply that you get maximal freedom in this supervisor. we don't. The idea is that here is that the supervisor should not unnecessarily restrict the behavior. So this is a safety procedure in the sense that, okay, it gives maximal freedom to the plant, but still guaranteeing that you have a plant that is controllable and it's non-blocking. So this is then called the maximally permissive, controllable, and non-blocking supervisor generation. And here comes now an example how this works. But I think that we take a break here, and I will show you this in the afternoon here. And I will show you some other examples too on this algorithm. And finally, I will also show you how we can actually generate these original forbidden or uncontrollable states when we synchronize P and SP, which is another tricky part in this algorithm generation. But I think we stop there. And then let's see if you have any questions.
Thank you, Professor. Participants, if you have any questions, please put on the chat box or you can unmute yourself. And meanwhile, I request you all to please start your videos so that we can take a picture. I request Samir to, good evening, ma'am. So,
good evening, ma'am. Good evening, sir.
Yes, sir. So you are from electrical engineering?
Yes, I am from electrical engineering. We have the electrical and computer engineering program in our institute. So this is a new field, and we have introduced this course on AI.
Okay.
So I did my ME computer science, so I have an interest in this field. Otherwise, I am working with soft computing.
Okay. Okay, very nice. So any questions you have?
No, ma'am. It's very difficult to understand these logics.
Yeah,
so we'll study. We'll study first, and then we'll be able to relate what we have studied with Dr. Bengt.
Yeah, that's very true. So one question that I had in my mind, like when Professor, you said that it is related with the Nash equilibrium problem. That did not immediately click to me. I could not relate it with how that was related with, that was equivalent to or something close to Nash equivalence, Nash equilibrium. Yeah. Although when you showed the proof, you praised the proof, some vaguely I could understand that how it is understood.
And I have to admit that first, we can say that, the connection to Nash is quite weak. It's more that, okay, this is a game problem. And for those of you who are in strong on formal methods and etc. in computer science, then you know that computer scientists love to formulate things as a game formulation. That I realize that, and sometimes I must say I'm a bit surprised, because I think, why should you formulate this as a game? Why there is no meaning for this, but still people do that. But there is absolutely a meaning to formulate it as a game when you come up with these, so to say, environmental behavior where the environment can do things which you must be able to respond to. So it's a kind of fight. Okay, you do that and that, and the supervisor must be able to follow that. That can be considered as a fight, and then it's a game. But the connection to the optimality, the Nash optimality, is not obvious. It was just that I would like to relate to game theory in general. That's why I mentioned about Nash. But so don't think about that. But generally, game theory is a fight between. You could say that a very traditional game formulation is that you take this every second time. Okay, now to player A and B. Now player A can do make a transition, and after that player B can make a transition. And by doing that, the question, how can we guarantee that we still have some good properties? That is one typical formulation of game theory in computer science, and you could say, I mean, in AI related stuff. We don't use to formulate it in that way in my community, but when we look at our results, we can say, oh yeah, okay, we can consider this as a game. Actually, I found that in a new book on model checking quite recently. It's a book that was published just 2 years ago or something. It's a very good book on model checking. I should maybe I could introduce a reference to that book this afternoon. And when I looked at some of the later chapters there, and they start to talk about synthesis. And then as soon as they start to talk about synthesis, they also included actually this concept of uncontrollability, which was a bit of a surprise for me. So it meant that, oh, they have actually brought up something we have formulated a long time ago. And now they say, well, this is a game. Yeah, of course, it's a game. We haven't called it a game, but they call it a game because they find it natural. Okay.
Yes. Any other question that you have, participants? If not, once again, I request all of you, Samir, Purnima, please put on your videos, and Shubhangi, take a snapshot. And thank you all the participants. Now you can relax, you can go home, have tea and coffee with your family and friends. We will be meeting at 6:30. Okay.
Yeah,
so
thank you very much.
Thank you, Professor. We will be meeting at 6:30 Indian Standard Time.
Yeah. 3 o'clock for me. No, how is it now? Okay, I will come. I will be there in time. Actually, no, it's 2 o'clock. It's 2 o'clock for me. 2 o'clock for me. Okay, see you then.
Yeah, 2 o'clock.
Bye-bye.
Yeah, see you back. Bye-bye.